All right, hello engineers. We're going to go through an exam waste question from last year. I'm going to make it a little bit harder though. I'm going to add a couple of point loads in. I'm going to add, because we need to know how to deal with point loads and UDLs at the same time. And also, wink wink, this makes it a little bit more like your upcoming exam question. So we're going to add a 500 Newton force here at the beginning of the UDL. And we're going to add a 900 Newton force here at the end of it. Now this question here, if you read it, it says there is a 150 kilogram load that includes the mass of the bar. It's distributed evenly over a 1 meter length between points P and Q. So there's a UDL acting here, and its value is 150 times 9.8, because it's in kilograms right now, newtons per meter, which ends up being 1470 newtons per meter. Okay, so that's just that 150 kilogram load that's spread evenly over the 1 meter. I've just times this by 150 to get, sorry, by 9.8 to get 1470. So we've got a UDL that's 1470 newtons every meter acting in between these 2 point loads. Okay, now you'll notice that it's not symmetrical. There's a 0.3 meters here and 0.2 meters here. And this results in a reaction that I've already calculated of 1670 upwards there and 1200 newtons here. So in this video, I'm going to go through a really quick and simple method of calculating, coming up with the calculations for your shear force and bending moment diagrams and actually completing them. It does make your life there is a little bit of a clunky way that we have to end up using in order to calculate our maximum bending moment. In other words, where that acts and its value. But overall, I think it's a little bit easier. If you're comfortable with your old method, stick to it. But here's a new and easy method. Here we go. So when we're calculating shear force, we're going to start with shear force. What we need is, so obviously you're going to have to start by calculating these reactions. That's what you're always going to have to do. But I've already done that for you. So I'm going to calculate my shear force. My first shear force, V1, you guys should know this. It's the value of our first reaction. So it's 1200. 1200 newtons. Okay, so I'm going to put that in here. 1200. So that's 1200 there. That makes that 800. And then that makes that 400. Minus 800. Now, if you're going to succeed in doing this method, you really need to know, well, how shear force and bending moments change under given loading scenarios. For example, we know that shear force, or you should know that shear force stays the same if there's nothing acting on that segment of the beam. So between A and P, nothing is going on, so shear force will stay the same. So we know that V2 equals 1200 as well. Or we could just say that V1 is this acts up until point P. Okay, so up until here, V2 is remaining the same. So we can put that in, and we can go ahead and draw a straight line straight between them. Done. Now, you should also know that for shear force, when a point load acts, the value of the point load will push it down or up the exact value of the point load. It's really that simple. So my calculation is going to look like this. It's going to look just like this. V2 is going to be the value of my last shear force, subtract the value of the point load. Unless it's going upwards, in which case you would have to add. So 1200 take 500 is 700 newtons. So I know that right here we're going to have a value of 700 as well. So I can go ahead and draw a straight line between those. just like that. Okay, now here's how we know that shear force acts over a UDL. It acts linearly, and it acts just like this. So my new calculation for V3, and V3 is going to be right until the new point load acts, so it's going to be across the whole distance of this point load, of this UDL, sorry. V3 is going to be the value of my last shear force, which is 700, then subtract the value of the point of the UDL, which is 1470 newtons a meter over X meters. And in our case, that is 1 meter. So it's just 1470 times 1. So if this was, say, a 500 newtons per meter load over a distance of 2 meters, it would be 500 times 2. You know that to turn a UDL into a point load, it's the value of the UDL times the distance it acts. So 700 take 1470 is minus 770. So I know at the end of this UDL, when this next point load acts, which is right here, my value is going to be minus 770, which is something like that. So now I'm going to go ahead and draw a straight line between them because I know it's going to be a linear thing. And we're nearly done already with our shear force. So V4, again, it's going to be the value of my last shear force, which is minus 770. And I'm going to have to take the value of the point load that's acting there, which is 900. So it's going to be minus 1670 newtons. So this is going to drop to minus 1670, which is somewhere there. Draw a straight line between those. And I know that that's going to remain the same until my new final point load acts. Which is right here. So it stays the same, and then it's going to be bumped up to 0. I could do a calculation for that. It's really going to be a formality, but I think it might be a good thing for you guys to do. We could say that V5 equals the value of my last point load, last shear force, sorry, plus the value of the incoming point load, which is 1670, which equals 0. So that's a bit of a formality, but there you go. So there's my calculations for shear force. Very simple. There's one more thing we have to do, because we know that in the future we're going to have to calculate the point of our maximum bending moment, and this is going to be, you're going to have to do this every single time. And in order to find the maximum bending moment, we need to know where the maximum bending moment is, and we do that by finding out where our shear force is 0, because the shear force is the differentiation of the bending moment diagram. So we know that when the differentiation of a function is 0, that's where the turning point is, right? So that's where our maximum is going to be. The maximum for our bending moment is where our shear force is 0. So we've got to figure out where that is. And here's how we do it. We're really going to go back to Year 9 algebra here. So take off your engineering caps for a moment and think about it mathematically. We're going to figure out where this thing hits 0. So we're going to call this point here the start of our line. So this is x equals 0 for this case. So we could say that V equals the start of our line, which is 700. This is going to be the equation for the line here. 700 subtract the slope of the line, which is 1470 newtons every meter over x meters. So there's the function for my line, and that's going to be important later because we're going to come up with a function for our bending moments. But we can already use this thing here to figure out where V equals 0. where our maximum bending moment will be by plugging in a 0 value for V. So 0 equals 700, take 1470x. So x has to be 700 divided by 1470, which gives me 0.48. So the distance between here and our 0 value is 0.48. But that means that the actual distance from here to the end of the beam is going to be 0.48 plus 0.3. So it's going to be 0.78, and we're going to mark that in right here, 0.78. We know that that is where our maximum bending moment is going to be, so I'm going to mark that down here as well. Okay, so I'm going to leave this bit up here because we're going to have to refer to that in a bit in order to calculate our bending moments. But I'm going to leave this video here. I'm going to get rid of these shear force calculations and start again for our bending moment calculations because we're running a little bit out of time here. And I'm going to show you not only a quick way to find out a couple of bending moment points here, but also a quick way to find out what the maximum bending moment is. It's a little bit clunky, like I said, in the same way that this is, but if it means you can do these calculations this simply, then it might be a good thing. It depends on your temperament. Okay, so hang in for the next video where I show you how to do the bending moment diagrams in this method. Okay, much love, bye.